in 1 hour. And if you have questions, you can email me at tulsi.tulasiram@humanitoba.ca, or you can visit my website to see other similar projects that I've been working on with my team here. So the question here is, why price? That's the thing that we need to first ask. What do you want? What is the motivation for this talk or this research? Right? What is meant by pricing problem? I mean, how do we define the problem? We have to define the problem only with which we can say go ahead further, right? And price with what? That means what is the technique or the methodology that we would adopt in order to price this, say, product. It's a product. Option is a product. Right? Then how to price? That means how do we really implement the technique that we decided to use for this pricing problem? That means mapping the technique, mapping whatever the technique that we're using, that is the Firefly algorithm, and implement it on a platform, computer platform, and then do experiments, right? And then how do we make sure that what we get as results are correct, right? That means how do we evaluate? So these questions we are going to ask, and then we'll answer as we go along. And before I start the talk, let me quickly give a brief intro to my university. Of course, we are in Canada. So Canada, as we know, is a very vast country and the second largest in the world after Russia. And we share a very long border with US, south of us, right? It is about 9,000 kilometers border all along. And Manitoba, the province, is the center of Canada. And Winnipeg is also almost the center of Canada. It's also, geographically speaking, the geomagnetic center of Canada, or North America rather, right? And Winnipeg happens to be the largest city in this prairie region, and until 60s it was third largest city in the country, Canada. So Winnipeg is just 1 hour north of US border, and the closest larger city is in US, that is Minneapolis. Toronto is by flight, it is 2.5 hours, or if you want to drive, because this region is completely, say, forest, mountains, and lakes, so it's only a 2-lane undivided highway. It will take 20 to 24 hours, right, non-stop driving. And of course, Manitoba extends all the way to another border with another, say, territory, Canadian territory called Nunavut, and which extends all the way to North Pole. So if I travel about 4,500 kilometers from Winnipeg, I will reach North Pole. I had to travel 13,000 kilometers to reach Madurai. Right? So Winnipeg is in the southern part of the province and has two rivers, which are the Assiniboine River coming from west, and the one coming from south in US, in South Dakota, is called the Red River. They join in the place. Of course, they start settling at that particular, say, junction. It's called a fork. So it's a major attraction in the city. Is downtown Winnipeg, right? So these two, then this Red River goes further north, flows further north, and say dumps into the Lake Winnipeg there. So we are somewhere down here, University of Manitoba, in the southern part of the city, close to the, say, the perimeter highway, or whatever the highway that goes around the city, right? So it's near the southern end of the city. It's tucked in by the Red River. Very beautiful campus here, huge campus. We have two campuses. This is the main campus, and the medical faculty is in downtown, attached to two hospitals there. Right? So that's another campus. So this is the main campus. We have all the different faculties here: arts, engineering, business school, science, kinesiology, architecture, music. You can say agriculture. Multiple different faculties here. So most of these are, except for medicine, like they're all here, right? University of Manitoba. We have a very nice bombers play here, and then of course we have multiple different. Okay, so I'm fortunate enough to get lots of students in the past 2 decades to train in various different topics of, say, financial problems as well as cloud computing problems, research problems. And two members who are directly involved in the current topic are Mr. Govindpreet Singh, who finished masters on this topic, and then Dr. Premala Tulasaraman, who is a colleague, and also my wife, who is also a professor in the same department. Okay? And of course, there are multiple people, and I had visitors coming from India in various scholarships from their country. And of course, my students are well settled. For example, Raja Padu is a professor here in University of Manitoba. David Alonator, he went back to his country, Nigeria. He's leading, I think, in top management position in his university. And a recent graduate, Eid Al-Balawi, he's from Saudi Arabia. He went back to his country and he's doing very good. He's also in the administration there, I think, associate research vice president or something indirectly. And Kiran is one of the senior managers at SAP. Likewise, there are other students who finished, and their manager, Samir Kumar, who finished. He's doing the trading, electricity trading, right here in Winnipeg. Banu Sharma, he's in Toronto. He's also doing very good in his financial, company, whatever that company that he's working in. So there are multiple, students. And also I've been fortunate enough to get funding from various agencies to support these students and visitors. So the major one is the so-called Discovery Grant that is given, as of course, all of them are on competition basis. They're all highly competitive. So the Natural Sciences Engineering Research Council of Canada program has multiple programs. The main one is the Discovery Grant. So everybody has to apply. So with this, without this, getting a tenure or promotion is impossible. So this is almost equivalent to our CSIR, Council of Scientific and Industrial Research in India. And then it also has an Engage grant. So this is a pure research grant, pure research, right? But this one is industry, direct product that we had to make it commercializing, right? So we had opportunity to get a couple of industries participating with us. They don't possibly have many times researchers in their team. So we provide our students and work on their problems and work with our ideas, right? But then at the end of the project, entire intellectual property is transferred to that company. Then the university has research programs. So there are a couple of research programs which I have been able to get. And also Bachelor of Science, in which computer department, they have so-called interdisciplinary research program. Through this, I actually work with people in science, math, and statistics, in business school, basically finance and management, and in agribusiness and agricultural economics, in engineering. And my tax Accelerate is also an industrial project. Here, this industry doesn't have to pay anything. They only participate. They don't make any monetary contribution. They only provide their personnel to get trained. But here, my tax Accelerate program is supposed to provide us 50% of the funding, and the my tax provide the other 50%. If there are students in audience right now, undergraduate students, this is a very good link for them to look into. So if you want to come to Canada for graduate program, master's or PhD, if you're an undergraduate, you should be an undergraduate student. The so-called the Global Link Research Internship, GRI, is a very attractive program, and it's a 12 weeks, all paid, right? Visit to Canada, any of the universities that you wish to go. And of course, there's a process. You can read through the process here. So let me not explore that right now because of time. So of course, there are other funding agencies. So with this funding, I support students to get multiple different projects done. So let's get to our topic here, pricing financial options. Right? So let's first see, when we say financial market, right? First thing that comes to mind, of course, is the stocks, right? So how option is different from stock, right? So let's quickly see an example. That way we can explain what option is and why people go for option and what's the motivation to, price this option. Of course, we'll explain what pricing means. So let's look at this loss profit scenario with a stock and option. Let's say a particular stock is $50 today, right? So of course, in 1 month, it might go down to $20 or it might go up to $80, right? In one month here. I'm just picking up some numbers there, right? So they're all nothing meaning, but just for understanding purposes, right? So with stock, if you have invested $50 and if it went down, you lost $30. The loss is 60%, right? If the stock price went up to $80, of course, you profit, right? $30, which is also 60%, because your initial investment was only $50 to buy this stock. Okay, let's look into option. Option actually is a contract. It actually happens in India at the very low level. Like when you want to build a house, right? Your contractor will have some sort of an agreement with suppliers, either sand, cement, or say the iron, raw materials. Right? They always have, okay, based on the start of the project, in 3 months possibly I'm going to need this much of cement or this much of say iron, right? They will have some sort of contract there, right? So it's not say fully honorable, whereas these options, right? So those are actually options. These are also options, but then these are all bound. Like so once you enter the contract, you are bound by the regulations of the contract. So let's see what an option is. Option is basically a contract, right? In order to buy the same stock, right? You're not buying directly, but you're going to buy it at a later date, right? For a later date, you have to fix a price, right? So you fix this price called strike. It's called a strike price, or the price at which you're going to buy in the future. That's $60, let's say, right? Just a number again. $50 today's price of the stock, and 1 month later, I'm going to buy at $60, right? So with that, because I'm getting the right to decide at 1 month later what I'm going to do, right? I may not buy. I don't have to buy. If I don't have to buy, that means that person hoping to sell it to me is kind of sitting idle, right? He loses the business. So in order for that to avoid, I have to pay that other party a premium. So the premium is let's say $5, about 10% here, right? So that is fixed by the other party, the premium. So that's my only initial investment, right? And the strike price is $60, let's say. So when the price goes down, what I will do is, of course, I'm not going to exercise my contract. That means I'm not going to buy the stock from my contract, because in the open market it is selling at $20. If I have to buy through this contract, it is going to be $60. Why do I pay 60 when I can get the same thing at 20, right? I don't buy it from my contract, so I will let the contract die. But the $5 initial investment that I made is lost, right? That's my loss. Of course, 100% loss, because that's the only investment I had. In the other case, when the price went up $80, right? Initial investment is still $5. Strike is same $60. What I would do, of course, because it is $80, I will exercise my contract. That means I will buy through my contract at $60. That's my fixed price, right? And I see that a very good opportunity to make profit, because the open market it is $80. So I can quickly sell it and make $20. Of course, I made $5 premium paid before, so I make profit of $15. So $5 investment, $15, say profit 3 times 300%, right? So why not everybody go into that option, right? And one thing is, okay, one other point here is like even that $5 can be regained, because in options, normally you don't buy one stock, it's generally 100. One option is normally 100 stocks. So to buy, say, initially 100 stocks, you would have spent $5,000. But here you're not putting this $5,000 like out, like you're not spending it. So you hold. You can always put it on some simple interest, like keep that idea interest, right? To generate some simple interest. It will easily generate, say, $5 in a short period of time. So that $5, whatever premium you're paying, can also be recovered from this initial, say, deposit of that $5,000 into simple interest. Right? So that way you really make $20, right? Though I'm not, say, including that. So why then people don't go for options? Of course, they do go for option. If it is so good, right? Why not everybody go? The thing is, this is only a speculation, right? It's one side. It might go up, right? It might go down as well. So you have to consider both possibilities. So in order to consider both possibilities, what you have to do is, when you take one position of, say, buying the option, you have to take opposite position as well to avoid the risk, to consider possibility of the other scenario, they're losing, like the price dropping down, right? So that you can balance out. So instead of just going one contract, you'll sign a contract with another party to sell option. You may have it, some other option through that contract. So likewise, people who are real investors, get into hundreds and hundreds of such contracts, right? So sometimes they get lost in the tracking of all the different products that they have signed in. So they end up losing if you're not good at carefully monitoring. So in 2008, that's what happened, like a huge loss in the market because of this kind of collapse. Okay, so let's quickly recap. So financial option contract is a type of contract between two investing parties, right? First party, the buyer, you'll get the right because I'm paying the premium, I will get the right to buy or sell depending on what the contract says, an underlying asset, a stock, at a particular fixed price, which is the strike price we said. Specific period of time, that 1 month. Second party, the other party, who is known as the seller or the writer of this particular option, because he's the one who write about the premium, is obliged, of course, to decision of the first party. So if I decide to sell, if I decide to buy, right, through the contract at $60, the other party has to sell it to me, right? Though he can sell in the open market at $80, right? He cannot do that. He has to sell it to me. If he has more, of course, he can sell, right? Whatever I want, he has to provide. So the other party is obliged to say, sell me the stocks because he took the premium. So the holder, of course, I pay the premium to the writer at the time of getting into the contract. Okay, there are two types: buying and selling, right? So why it is called a call option for buying means I have money, I want to say buy something, I'm calling whoever is want to sell, right? So it's a call option. And I have some stocks, I want to put it away, I want to get rid of some stocks, right? So it means I want to sell some stocks, so that's known as a put option. So only buying and selling, call option, put option. So this whole presentation is going to be on easy to understand is call option. Put option requires some relative thinking here. So yeah, you can still make it up, right? So both call and put options. These two options can be exercised in multiple different styles. So those are different styles of options. I think I skipped that slide here. Anyway, I think it may come. So what are the different parameters that involved in the option pricing? First of all, initial asset price, that $50 we said, strike price, that $60 we said, contract period, that 1 month, volatility, well, I'll come to that in a minute, interest rate, remember the interest that I mentioned before, the initial spending that you're not doing, you can put it in simple interest that can generate some simple deposit that can generate some interest, right? But this interest is basically bank-to-bank interest. And volatility is the degree of the price movement. Of course, price is not staying constant, right? It's always moving, right? So you have to look for the best time to do your exercise. Exercising means buying or selling through the contract. So that's the moment that you have to be watching. Of course, some option doesn't give you that opportunity. Some other option contracts gives you that opportunity to grab the particular moment, right? Okay, so I think get into the styles soon. Yeah. So the option. What do you mean by pricing, right? So that's a big question now. With the title, pricing problem. So we explained what option pricing is. What is option pricing problem is for research purposes, right? So the brief statement here is that predicting present value, present worth of an option from any future of the contract, right? So what is any future, value of this contract? So the $20 we said 80 minus 60, right? The $20 minus $15. That is happening 1 month later. What is the value of that $15 now? How does it compare with the premium that is being asked by the other party? So whatever the present value of the future payoff, I'm going to use the term payoff, that's what it is. So the K, S minus K we said, right? S is 80 minus 60, right? So as that is the so-called the payoff. It's coming up, but the payoff is happening in the future. So what is what today, right? That's what we have to find, so that we can compare it with the premium that the other party is asking and decide if the premium is high or low, then decide to enter the contract or not. So the pricing problem is finding the what of the payoff that is coming from a future time. This is a present, predicting the future present value from a future payoff. That means you have to speculate the asset price, where all it can go. From $50, it can go stop at 60, or it can go to 80, or it can go to 100, right? So you have to speculate. So you have to have some sort of mechanism in order to simulate the price path, how the stock price could behave, right? So for a call option, we did S minus K when you want to buy. For a put option, it is other way, 60-20, right? 60 minus 20, 60K, S is 20, so K minus S at that point. So only then, because in the put option, if I want to sell, I want the price to go down, right? So that through this contract, I will sell it at the contract price, which is $60, while at the open market, if I have to sell, I have to sell it at $20, right? So I make that $40 in through put option, right? When I sell it. And so how do we say exercise this option contract? So what are the different possibilities, right? There are multiple different ways, styles we call it. So European option, American option, and others, right? European will allow you to exercise only at expiration. So 1 month means you have to wait for the month. So even if there was better opportunity in between, you cannot, right? You have to exercise whatever is possible at the end of the month. Likewise, American, of course, gives you that, say, freedom to decide whenever you want to exercise during that contract period. You don't have to wait all the way down to the end of the period, right? So you can do before the expiration of the contract, right? That's the American option. Of course, naturally, you can immediately get the idea that because you're getting a better freedom, right, better rights, you may have to pay higher premium, right, with the American options. Again, one more point. The names European, American has nothing to do with geography. It's not that European option is available in Europe, American option is available in America. No, right? It is only names, just names. So like what is Asian option? So Asian option gives you multiple opportunities. Instead of giving you one opportunity in American, Asian option gives you multiple opportunities in between. So if it is a 3-month contract, the contract might say you can exercise either at the end of first month, or the second month, or the third month. So between start and end of first month, it is like a European. Between first and second month, it is like a European option, right? So multiple European option put together is Asian option. Russian option is the period itself, the contract period can itself be, say, moved around. So barrier option, you set a barrier. So once the price crosses that, I will exercise, right? So you kind of make it automatic, right? That kind of thing. So there are many other such styles available. So we consider only these two, European and American, for pricing options in this case. And what are the now? So once we define the problem, once we define the various say types and styles, we have to know what are the techniques available to do the pricing, right? That's one of the questions that I had. I'm going to summarize that at the end, right? So the whole pricing problem became imminent in 1973 when 3 authors like Fisher Black, Myra Soles, and Robert Merton, they say based on original theory proposed by a student in the University of France in 1900 in French, of course, right? So it's called, his name is Bachelier. So he proposed the idea of this option in 1900, right, formally, right? Of course, nobody knew until 1960s when MIT professor took it up and got it translated, and then saw the beauty of the idea. And of course, whenever you have, say, investment, there is always risks involved. So these authors try to, say, eliminate that risk. That is the beauty of this model, 1973. So when it got published 1973 and people really tested it or accepted it, a huge market was opened in Chicago. That's a Chicago Board of Options Exchange. So it's a $1 trillion market started on options and on multiple different products. So Chicago is the main, say, center, say, for all this commodity trading, right? Most of the commodity trading happens there. So they found a closed form solution for this option pricing problem. Actually, the formulation itself was a stochastic partial differential equation, right? It's a partial differential equation. So they have to solve it. In order to solve to a closed form solution, that means like a formula, they have to make one major assumption that volatility is constant. You see, that is a major assumption. Volatility cannot be constant, right? Volatility, I mean, the price keeps changing, right? Volatility is always high. Better the volatility, better the opportunities for making profit, right? So also they could price only European option. They could not do it. Of course, then there were modifications to this model came up by students, by these two and other people, which allowed to do pricing of say other styles of option. And this model, Black-Scholes-Merton model, won Nobel Prize in 1997, and of course by then a much improved model with the relaxed, say, condition on the volatility has already been in the market. It's called Garsh model, right? Generalized autoregression conditional heteroscedasticity model. Skedasticity is the fifth one in statistics: average, standard deviation, skewness, right? All those, the fifth one. So that model won Nobel Prize in 2003, right? So that is in 1973, this first model came about. And of course, people in finance, right? They're not into differential equations or solving equations like that. Right? That is the engineer's job. Like the title I mentioned, CFD, right? If your engineering inclination, if you have that engineering inclination, CFD would mean that computational fluid dynamics. That's what I was doing before, right? So I'm used to see these differential equations, partial differential equations. So we use techniques such as finite differencing techniques to solve those equations for, say, well, not closed form, approximate solutions. Of course, this is closed form solution. So we used to deal with what is known as Navier-Stokes equations, right? Which is similar to this Black-Scholes equation or Black-Scholes-Merton equation. Anyway, so the researchers in finance, they're not they're exposed to these mathematical, say, generalities. So they developed their own, say, idea by, say, discretizing the time. So Black-Scholes-Merton model is a continuous time approach. That's why it is ending up with a differential equation. Black-Scholes, the binomial lattice is discretized time. So they kind of see, okay, from today, how the price will change. Either go up by a factor U or down by a factor D. From tomorrow, another factor, same factor. Need not be same factor, but they assume same factor by U, another factor by D. Likewise from here, U, D. At every step, that's it. So if this is a 3-month option, you can say that, oh, in 1 month the price change, this happens, or in second month this could be the cases, in third month these could be the cases. But then you are skipping so much within the first month, so much within the second month, because price change doesn't happen just only at the end of the month, right? It could happen at another week, no. It could happen at another day, no. It could happen at another hour, no. It could happen continuously, right? So if you keep these time steps so small, you can try to replicate the Black-Scholes model. That was their idea, like the binomial lattice model. It was very successful and it is accepted as their own, but engineers would suggest that, oh, this is nothing but our finite differencing technique that we use, right? So if you make a simple mathematical, say, transformation, we can represent this triangular, say, structured, say, tree-like, say, structure into a 2D rectangular grid, which is basically a finite differencing technique that I used to do, right? So that's how I got into easily these kind of problems. So if computation becomes intensive, if you have like this, so the number of nodes that you have to price runs into millions. So you have to employ, say, super fast, say, supercomputers. And at the same time, this happened in 1979. At the same time, Monte Carlo simulation was introduced. So this is a structured way of the price evolution, where instead of allowing the price to say evolve structurally, why not make it random, right? Like in the reality. So start from one price, so let it go, like change, keep changing, right? But just with one path, you're not going to, one random walk, you're not going to see the reality. So you have to generate like millions and millions of such random walks, and check the prices at each of the path, end of the path, and then take the payoff, and then do the, say, discounting to get the present value. There also computation is intensive, right? So these are the classical techniques, and this is the formula that Black-Scholes model provided. Simple formula: plug in these numbers or these variable values, and then you have the call option price or the put option price. So this is what we used and became very popular as Black-Scholes computer in handheld devices when the Chicago Board of Options Exchange opened in 1973, right? So it's very popular that way. And then we have to look into some unconventional option pricing techniques. So these days it's mostly AI driven, artificial intelligence, like neural networks, deep learning, machine learning, all these things. Right? And then of course people started looking into some bio-inspired, such as the genetic, like how genetic algorithms could be used for this kind of problems. These are used in other research areas. So why not look into in finance? Like of course curiosity, right? Research, curiosity-driven research, right? And I mentioned curiosity. Is these things necessary? I'll answer that question quickly. So the third one, of course, is nature-inspired computing. Of course, how animals, insects in nature behave. For example, ants, how do they behave? Bees, birds, how do they behave? How do they swarm in order to reach their food source, right? And what we are going to study is Firefly algorithm. Firefly, of course, in the night they glow, right? For a particular purpose. We'll see how we can try to use the glowing phenomenon of an insect, and we can map that for doing this pricing, right? We'll see that. So, as I asked, are these things necessary? Okay, when will these become necessary? Okay, because these are all going to give you only approximate solutions, whereas the Black-Scholes closed form gives you the accurate solution, the so-called the deterministic, say, solution. So only for problems for which you cannot find deterministic solution in other areas, generally they employ this kind of heuristics techniques, right? Whereas in general, in computer science, we don't accept heuristic techniques to be used when you have deterministic solution, right? Why go for approximate solutions when you have accurate solution, right? So that's the question. But then we keep that aside, because whatever you call accurate using any other classical techniques is not going to be accurate enough, right? Because it is so uncertain that the price changes happening will immediately collapse your, say, whatever, say, price prediction that you are making with any technique. So that way we argue these techniques need to be studied. So that's how this area flourished. So these are all called, the last two areas are called computational intelligence techniques. Like this is more like a machine learning technique. Okay, let's look at the current study now. So we are getting into why use these ideas, right? So why price the algorithm? So we want to compute the prices accurately. So that means we want to formulate the problem as a multi-objective optimization problem. I'll explain soon. And we design and develop an algorithm based on Firefly for this option pricing problem. And then we make sure that the results we're getting are, say, accurate enough within certain small error bounds, right? When compared to the real data. Real data means what happened in the market, real market. Okay, let's quickly get into the Firefly algorithm, what it said. It was, say, proposed by a researcher named Ang in 2008. It's inspired by the unique, say, flashing behavior, light behavior of, say, fireflies. Fireflies we would see in rural areas. If you go, it'll be glowing, right? So they have two purposes. One is to attract mating partners and warn potential prey, right? So if the brightness is really good, the intensity of the light is high, that means you're being attracted So if the price is good, if a particular, say, stock price is good, more investors are attracted there, right? So it's one direct mapping that we can see high level, but we have to bring it down to model and equations in order to get a result out of it, right? So that's one thing. And also one potential prey, right? So the people, the other bigger bucks that trying to eat this, say, Firefly, has to be warned away by some other means. So that means bigger investors who kind of try to take away. So you saw the recent history. I mean, recent happening GameStop, right? So kind of big ones try to stop trading and all that. So these things happen. So they want to warn. So unless these small investors took flags like protest, these people didn't. They were doing silently, suppressing the market, right, in the GameStop. Likewise, so one potential prey that could be another purpose for this glowing phenomenon. So people have used this in other, say, research areas, right? This particular heuristic algorithm, and used it in many real world, and they found it to be efficient to, say, use them. But of course, each problem will have a different, say, means of mapping the phenomenon from Firefly to a particular problem. So I explained brightness here means attractiveness, that means better price, and also brightness means it is kind of allow some praise to, say, suppress the market, right? So both are possibly seen here now. So we are trying to use this for pricing options, right? So let's explain what Firefly algorithm here means. So you see lots of fireflies, flying around and trying to reach the center, which is the most attractive part. So the light intensity of each firefly is going to be proportional to quality of the solution here. And that means attractiveness is directly proportional to the brightness, and attractiveness is also, of course, inversely proportional to the distance. If you are too far away, you're not going to be attracted, but then you may be attracted to a nearby other, bright, firefly. What do you mean by that? So if you are interested in one particular market, like a technology market, like all the technology stocks, right? So you look mostly for that kind of thing. You are closer to that market, whereas you will not be worried too much about the petroleum market, right? Whereas if you are looking mostly for a consumer product, right, you may not be looking for a forest product. So the farther you are going to be farther away, right? So it's as you farther from a particular market, the attractiveness is reduced, right? So we have two elements in the movement of these particles. One is approaching to a better solution, that is attracted to the best bright, firefly, and of course we have to move randomly. We cannot be going directly to that particular, because there is in between some brighter, say, objects, particles, which will attract you, though they're not the brightest, right? So you go there, then go further down. Right? So how do we model this, right? So we have option pricing going to be modeled as a multi-objective, as I said before. But here we are going to explore only two objectives, but each objective has sub-objectives, right? So we map the option pricing in a 2D space with value of the underlying asset. That's the first one, and the exercise time. We know when you want. So that two basic criteria. So we know what is the price and how long is the contract period. And then the objective is to improve or increase your payoff. That's always the case, dollar, right? And also try to improve the probability of achieving the better payoff. So, but these are kind of opposite to each other. If a price can go from 50 to 80, the probability of going from 50 to 80 is not going to be high. It's not going to happen that, say, easily. It will be small. Right? So if you see that if you need the payoff to be high, the probability of achieving the payoff is not going to be high. It's only small. That means if your aim is to make a lot of money, you should keep in mind that probability of getting that big money is going to be small. That means you are taking a bigger risk going for a higher payoff. Right? So that's a big thing that you have to keep in mind. So now slowly through the probability, we are bringing along the so-called the risks involved. Right? So it may not happen at all. So in which case you lose all your investment. Right? Okay, so here's the model. So that's what we explained here. So we create this so-called the fitness function in order to test our results based on this payoff and probability. We create this function based on these two. So if the price is 100, the probability of price reaching 150 is only small, right? Whereas probability of price reaching 110 will be slightly higher, right? So larger the payoff, smaller is the probability. So our main aim is to find multiple such possible solution, because though I say that it is highly risky, but there are people who wants to take risk. So those are called the speculative investors. So one other extreme, people who are kind of moderate in the sense like whatever is happening, I will just go by, and whatever is coming, I'm fine, right? There's a middleman. Then there are other parties who are not conservatives. So speculative is one extreme. Conservative is, no, I don't want to take any risk. I just need minimum, say, profit. I'm okay with that, right? So the moderate may take some risk. So the conservatives are always worried about their investment. Speculators are always worried about the profit, right? So two extremes. So there are multiple solutions possible in between, right? So that all the solution is known as a friend, like a warm friend, cold friend. We talk about the weather. So across this line, one says curve, when the friend has moved, that means we have gone through a warm friend, right? So temperature is rising by 5 degrees or something, right? Or cold friend, temperature dropping by 5 degrees. So likewise, we have a solution line, which we have a curve, which all the points in that curves are solutions. Not good for everyone, right? One solution may be good for one person, the other solution may be good for other persons. So if you're looking for high payoff, say even without doing too much consideration, that you're taking high risk. If you want low payoff, you can expect that the risk is going to be small, right? So this whole thing is known as a Pareto optimal solution. So Pareto optimal solution is basically a set of optimal solutions which will trade off objectives at different possible levels based on your risk level. So there are two different approaches how we implement this algorithm. So how to use this technique now. So we define the techniques, we map the problem, we map the technique to the problem. Now we have to really bring it down to equations, and so that we can write programs and run it on a computer, right? So there are two techniques. One is the weighted sum-based Firefly algorithm, which I will skip for sake of time. I'll explain the other one, the non-dominant sorting Firefly algorithm. This is an interesting approach than the weighted average. So weighted sum is simply to give weightage for payoff and probability, some weights, right? But how many weights you want to consider? Any. So you can give all 100% to payoff, right? And you don't care for probability. That means the speculators. You want to give only the probability 100% weight, right? Don't care for payoff or small payoff, conservatives, right? So those two different people. So then bring it down to a single objective, fx, and then optimize that, right? Whereas the other one, non-dominated sorting, we try to consider multiple solutions and then try to see how each one compare each other, and that way we can sort them so that we can pick the best for whichever condition means whichever risk level you are at, right? So we design for improving the efficiency of multiple objective optimization is based on the concept of the non-dominated sorting. I'll explain what non-dominated sorting means. So the main goal, of course, is efficiently find a complete set of non-dominated solution that represent Pareto friend. So we have two objectives. One is the payoff, the other one is the probability. In one point in time, payoff is better, the probability is okay, whereas another case, probability is higher, payoff is acceptable, right? So no one is better none of these two is dominating the others completely, right? So that's what we mean by non-nominated solution. I'll explain it with an example. So here is how we implement it now, right? The non-nominated sorting. So Firefly algorithm, we explain how to say use this to study option pricing. Now we have to bring it down to a model so that we can explain and we can implement it on as a programming computer, right? So we do some initialization, right? And then we had to find the, say, values. What are the input values for, say, studying this problem? Like, what are the 5 different parameters we mentioned before? For Firefly, there are also 5 different parameters, which I will list later, right? So some of them I did not discuss, but I will not have time to discuss them anyway. So, and then we try to set our solution space, because we don't want to see that, oh, $50 is today's price. I cannot expect the price to be $1,000 one day, right? It is not, say normal to expect such a huge variation, right? So I'll have to set a boundary. Maybe 50, 100 is good. Maybe 150, it might go sometime. You never know. So I have to set some sort of a bound, lower and upper bounds, to define our search space. I don't want to be searching for prices that is beyond 150 or beyond 500. No, for a current price of $50, right? I have to set the boundary, and then we initialize the particles, or these say Fireflies. That means there are certain characteristics of the Firefly, and I'll introduce in the solution space all these 100 different, say, I'll use, I think, 100 Fireflies, and then we evaluate the objective function, which I introduced already before. And the objective function is to combine the payoff and the probability, right? So once we set it and we find this objective value for the objective function, and see if that is satisfactory, right? Satisfactory means it is within my risk level and gives me profit, right? Okay, so then we go through the non-nominated sorting. So what is that, right? So here, let's look at this example first before we get here. So we have, say, multiple solutions here, 1, 2, 3, 4, 5. So I have 2 objectives. I can have multiple objectives here. So 2 objectives, say F2 is maximized, like payoff. Let's say we are maximizing payoff, right? Right, that's F2 is payoff. F1 is minimized. The probability of achieving the payoff is normally low, right? So we have 2 different objectives. I can have more, like I can add third dimension, like say cost, right? Cost of this particular contract or the particular pricing. I want it to be small, of course. Cost is not only monetary, it is also computational cost, right? I want to make that as a parameter now, right? Computational cost. So it means I want to finish my program sooner, right? My algorithm to be very effective in finding the solution very quickly. That could be one. I can say that, oh, I want to finish it within short period of time. Time now meets the contract, right? Though I may have 3 months contract, if I have an American, I should be able to exercise my options sooner. Right? I don't want to wait for 3 months. I want to kind of be able to exercise these options sooner. So the time suit here. The computational time is different from the physical time here. Okay, that's one. And I can suggest some other such say dimension. So I can have, instead of 2 dimension, I can have multi-dimension here. Anyway, so just explain with 2 dimension here. So we have multiple solutions. In this one, so let's say X1, solution 1, right? So is, when you compare its value for F1 is smaller than F5, right? So F1 is supposed to be minimized, so this is better, right? Whereas if you compare the value with F2, the other say function, X5 is higher than solution 1. That means 5 is better, right? Like same thing like 2 and 4, right? So some solution Xi is not worse than Xj in all objectives, right? So if we have multiple solutions, they cannot be worse than every other solution, right? Solution Xi is strictly better than Xj in at least one objective, just like what we have. So in F1, solution 1 is better. For F2, solution 5 is better. So if this is the case, we claim that xi is not dominated by x2. Like each other, they do not dominate each other, right? So what is better in one objective, the other one is better in another objective, right? So we collect such, say, solutions so that we can decide based on this solution what is better for my conditions, my risk level, right? So the cell population is going to be sorted according to the ascending order of non-domination. So the non-domination, how better it is. So if you focus on the payoff, so this is the ascending order of the sorting here. All right. So then we add these non-dominated sorting solution into a separate archive, right? And then we evaluate the so-called the fitness function. Fitness function is like what is the non-domination level of my solution and how many such solutions I have, compare them and see how far I am in the fitness, right? If I am well within my reach, that's good. Otherwise, I will not consider the solution. I will drop them, right? And then I will also do the fitness based on what is known as a crowding distance, right? So if I am a solution I, right, and there is no one around me, right? So I'm unique. I can claim that I'm a unique solution. So that's what we look for mathematically speaking. But then when you see, say, price charts for many stocks, you will see one particular time that stock kind of spikes and drops very quickly. And again go back to normal, right? Normal fluctuation. So that one spike, though it is very unique compared to other say prices, it is not a best thing. It is known as an outlier, right? So based on the distance, crowding distance, I can identify the fitness of a particular solution that I'm finding, right? So that's another approach. So let me not get into this math here. So once I archive them, fitness is completed, and then see stopping criteria, whether I reach my objective. That means is payoff is good enough for me, and with the whatever the probability that I'm expecting, right? Either I can keep that, or I'm going to run this program 200 times or 500 times, right? And that would be my stopping criteria. Once I reach that, one of those two, then I will exit the program. My program will finish. And once, if I'm not, I'll come back. I will add new population. That means whichever one has higher fitness will be the new set of, say, particles, or that means new set of fireflies to start the whole solution process. Okay, so I'll go along until my stopping criteria is met. Then I will exit. Okay. Okay. So, what is our experimental setup? So now, how did we do? So what to do is one thing. Now, what is our condition? So we collected these data for European option, S&P 500 data, and for American option, multiple different, say, mostly technology stocks, except for this Goldman Sachs, and for 6 months period. And then for the volatility, we did decimal constant. We took the volatility index from the CBOE, Chicago Board of Options Exchange. And these are the Firefly parameters. I said the 5 of them. So I didn't have, of course, time to fully explain them. There are a few things, the randomization. Initially, we randomized the particles. For that, we had to give some sort of number, and also light absorption coefficient we had to mention, and then what is attractiveness. So initially, so of course, this gets adjusted as you go along, right? And the number of, say, such fireflies 100, and then number of iterations for stopping criteria, I set it as 250. Because we want to find a Pareto multiple solution, I want to find all different possible solutions. I don't want to specify one particular risk that will give you one particular solution. I want to find all different possible solutions. Okay? So this is the first set of results for European option. This is using the weighted sum-based Firefly algorithm, and the red here means negative, and green means a positive error. So I don't know if you could see it. It's not that clear for myself. It's because it's so small. But the idea is that we can have a huge set of, each one is a solution, all these points, right? Whereas what you see at the bottom is the minimum payoff. Here is the maximum payoff. So this is the maximum error. So the error is going to be only 1% here, something like that here. And then minimum error here. So minimum error happens here. So when you expect a high payoff, so your probability is going to be very low. When you expect a low payoff, the probability is going to be high. Right? That's one quick observation. So based on your risk level, you can choose this number, this number, this number, depending on you are a speculator or a conservative. So the entire set of solution is good for anyone now, right? And we compared some values. The error was here 6.4, the absolute value error here. Right? And the same thing for American option using the other technique, the non-dominated sorting techniques. Also, it's the same thing we observe. Again, the absolute value error is much less, 0.44, right? At a particular, say, point. Or that's the overall, say, for comparing each of the different solutions that we have with the actual, say, a real value of the option, which is coming from Bloomberg data. Okay. So of course, I'm not going to explore the values here. So then we had to kind of present this to multiple investors. So we had to make it clear that this solution is supposed to take care of the risks that is involved, right? So what is the level of risk that you can take? So investor has to select a single solution, of course, from this observed rate of friend, which trades off the both the objectives, payoff and the probability. Map decision variable as the investment risk in this case, so that means each point identifies the level of risk that one can take. Right? Investor selects, of course, a solution from the Pareto friend on the basis of his or her risk-taking capability, and of course, probability of obtaining payoff is mapped to the risk level in this case. Right? And then we try to evaluate now, comparing with, say, other techniques, the classical techniques that I mentioned before, Monte Carlo, binomial lattice. We have developed algorithms for these problems, for the same set of, say, parametric conditions, and compare how Firefly provides or compare them. So the error-wise, they are very good for multiple different maturity dates. So they are very good compared to the other two techniques. And likewise, we also compared it with the Black-Scholes-Merton model. Right? That's one of the very classical model, and then we see that it is much better, this one. As we said beginning, like, why do I go for a heuristic when I have a deterministic solution? Deterministic also made many assumptions, like volatility was constant here. So here the volatility is not constant, so it captures each time the price movement happens, so that we can get a better solution. That's how we get a better solution in this case. Okay. So here are some conclusions. So we proposed a novel model for option pricing as a multi-objective optimization problem. We developed two multi-objective optimization algorithms. One is adaptive weighted sum, non-dominated sorting, and then our experiment showed competency of a model and the efficiency of our algorithms. And of course, in 99% of the experiments, algorithms were successful in capturing true option price, that means the real one, available in the market with the Bloomberg data, as a solution to Pareto friend. Also, the strategy of using historical contracts to approximate the current level of risk is very efficient. Here are some future work. I think I'll just skip it. The contribution is this of modeling, designing and developing Firefly, and evaluating the results compared with classical option pricing techniques. So how did we answer our questions? Why? Motivation was mentioned in slides 11 to 13. What is a pricing problem? That is, problem definition was available in 14, defined in 14. And with what we said, price with what? That is the technique, right? Methodology and the technique. That is our Firefly, which is 16 to 21 slides. And how? That means, how do we implement it? Because one algorithm could be done in multiple different ways. So we saw the two approaches. One is the weighted sum, and the other one is the non-dominated sorting. So there were 23 and 32, 22 to 32, and the actual implementation was done in slides 33 and 34. And how do we evaluate our results for exercising, when to exercise, based on the curve, whichever solution you want to pick, and how to avoid, how to be aware of risks, right, through the probability measure. Right? So I think I will stop here, because it's just past, I think, full 1 hour. So thank you. And if you have questions, you can ask me or you can email me at tulsi.tulsiram@humanityrama.ca. And this is my website. If you want to say read other papers, you can email me. I can send you, or you can always find them online. All the papers published are all online, right? So you can find them. So I think stop here and transfer the. I think I stopped. Should I stop sharing now, or
Yes,
I should? I'll stop sharing.
yes, sir. Thank you.
Okay. 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 If you have anyone questions, please.
Dear participants, if you have any questions, please ask. Okay, participants, if you have any questions or queries, please mail me or mail me to the sir, which he gave the mail address to otherwise, I will give the mail address. Thank you very much, sir.
Thank you.
Thank you very much, sir. At the outest, I express my heartfelt thanks to the guest speaker, Dr. Rupa K. Tulsiram, for his past experience in sharing the views about pricing financial options using Firefly algorithm. Your presentation will be very useful for all of us. Thank you. I wish to place on record my deep sense of gratitude to our college principal, N.S. Saravanan sir, and HOD Dr. Resami sir for their full support in conduct of this webinar. Thank you, sir. I take this opportunity to thank the management of Saurasha College for their wholehearted support and especially for Secretary Dr. D.R. Kumar sir. I express my gratitude to all my colleagues who has joined today, Dr. Ponraj sir, Dr. Gigi Bhuneshwari madam, Dr. Kavita madam. Uh, Please excuses me if I left somebody. Thanks for joining today's meeting. Actively participated and for their overlooking responses. My sincere thanks are due to my guide, Dr. L.P. Ramalingam, friends, well wishers, and knowingly helped me a lot for the successful conduct of this webinar in a short span of time. Thank you all and all. Thank you. Thank you very much, sir. Thank you, my dear friends and my students. Thank you very much.
Thank you.
Thank you, sir. Please fill the feedback form which shown in chat box to get e-certificate. Thank you, sir. Thank you very much.
Thanks, Kumar.
Shall we wrap up, sir?
No, it's okay. Nothing.
Thank you very much. Thank you.
Thanks, Lingo, for.
Thank you, madam.
Thank you, sir. Thank you, sir. Thank you very much, sir. Thank you.
Thank you. Thank you. Thank you.
Anime na okay. Anime na.